Okay, this should be another quickie. Just wanted to show you that I did that thing for a function, and I I chose to do it this way. I really want this to be private. I don't want there to be any possibility of some further derived thing allowing for someone to declare one of these things without having it allocated from me. So what I have here essentially is a list of all the known functions. Those are friends, and they have access to this destructor internally. Externally, the only access is through smart pointing. And I made the slope what I call sloped line, so the slope is assumed to be non-zero and non-infinite. This is not my function. That's one of the. I think finite means it's not a nan and it's not an inf. You can double check that. You see there's here negative inf nan. I guess you can use these fit maths to check to see if something is plus positive infinite, negative infinite, or nan. Nan meaning not a number, neither infinite, not finite, not positive, not negative, not anything. Now, first, let me just comment this away. In my graph thing, I have now, I can add points, or I can add functions, or I can add points and functions, and do whatever. Here I'm just adding a sine function whose amplitude is 120, and this is a wavelength 600, so that's the full breadth of the interval. So we should see exactly one wave plotted without lines in between, just the dots, 100 dots. So there it is. Okay, now this printout's incorrect. You'll notice I managed to flip the axes. I gotta do the same. This printout, in fact. That guy, it's easy to fix. So just put a minus sign for his, it's called update, and update cursor here. Yes, point cursor. I need a multiply of some sort. Or some way to set x and set y. Don't have anything. Let's set. What? What's the point? What's that? PT. I don't know what PT is. How about that? Oh, equals. This point, there's two. You'll notice there's two cursor position indicators drawn. One shows the cursor position in terms of the client coordinates. Nothing in terms of screen. There. Oh, okay, fine. And the other one is supposed to indicate the position of, now actually this one, I wouldn't mind if it moved around with the cursor, you know, to show you more easily where the cursor actually is, it's a little cross beam, and where that cross beam currently is indicated here. So that nearly 200 and minus 30, that looks right, see? And so if I wanted to know, I wonder what this point is, those are the coordinates of that point on the graph. And so on. And just to show that I can add two functions, add another one, a line, slope 1 because I want to demonstrate that the slope of that particular sine wave, now is it going to be 1 at x equals 0? No. This one's not going to be exactly 1. Slightly off. The slope is higher because it's not sine of x, it's some multiplier to make it have one wavelength, and also there's the fact that its height and so on. If I wanted it to have a slope of 1, it would just be sine x. No. But let me see now. Sine x. How can I do that with what I've got? This is the amplitude. This is the wavelength. And in order to make it have the right amplitude, the right wavelength, it's 2 pi x over wavelength gives you the angle, right? So the slope at x equals 0 would be the derivative of this, that would be cos, and out would come 2 pi amplitude divided by wavelength, right? So, and this would be cos. So to make that 1, we need 2 pi amplitude over wavelength equals 1. 2 pi a over L equals 1. So the wavelength we need would be 2 pi times amplitude, right? I think that's right. I know I did that quickly, but the derivative of sine is cos, and using the chain rule, whatever this multiplier comes out, and that's 2 pi over lambda, 2 pi, let's see, Yeah, there you go. Now you can see that it has a slope of 1 because this has a slope of 1 and they're exactly aligned at the origin. Okay? So it looks like mathematics works in a few cases. Now one thing I could do is I could add color to these functions. I could make that a pure virtual, say. You know. Force everyone to implement that. Now they could just return white, say, or they could return a parameter passed in. Or I could make that actually, I can implement that in the base. Doesn't have to be pure. It's not real calm. I don't have it now. So I'll start it as white. Doesn't need to be virtual. Yeah? Okay, so I don't need to modify these guys. That's available for everything. And then, let's say we make the straight line green or something. No, make the sine wave. I have a bunch of... I'm building some colors. Well, we'll keep it like that. Now, in drawing a function, I need plot point now to, no, I don't really need to do anything with that. I can swap out the pen is what I'm using, right? Not M. Font. And so I'll do this once. Now plot point uses the current pen. And brush, what does it use the brush for? Oh, the brush. Okay, no, that brush is the background color. It's making a mixture color from the current. I'm just using M pen. All right, no problem. I gotta get the old pen. Does this thing return it? Probably not. No, I don't want to do that. I'll have to trick it. Get the previous color, set that to that, and now I've cheated. And then, in fact, I could make a pen here. And that. I can do that way. And then, at the end, pen pre. It's cheating, I know, but it's quick and we'll see some colors. Like really, plot point should have take a color parameter. So now those are just regular functions of functions in the xy plane of a single variable. They're not, well, they are and they aren't what's called a parametric function. Every function f of x can be written as a parametric function, which is something that either you remember from school, or if you don't, you're going to find out very shortly. I'm going to make another class for parametric functions. Here we go. We got a green sine wave and a white line. Unfortunately, these aren't going to mix. It's possible for me to make these mix, but instead of using plot pixel v or set pixel v, if you use set pixel, it returns to you the color underneath where you're plotting, right? So you could make a mixture of that, whatever. And if I wanted to, I could play around with my sine wave. Maybe give it a higher amplitude. What's my limit? 300 to 270. Now it's not going to have a slope 1. Oh, is that amplitude? Yeah, that's amplitude, that's wavelength. So it's way off, goes outside. 270. Oh yeah, that only goes to 200. 170. Now I removed anything to do with motion. If we wanted to make a sine function that's shifted, right? I haven't done that here, but I could add something like this. Set the initial angle, theta, and add a new member. What did the user call this? The phase. Phase angle, which is just added to the argument. Which we will set normally to 0. Could add another create call, but I'll just call this function. What would it be? Oh, I see. But this is not a, I'll have to cast it. No, I could do that. I think that's a fair cast. This thing returns an hi function, not a sine function. But I know that it is, right? I could make it return one of these. Right. It is returning one of those. Now it's just a regular pointer. What do I want to set it to? Let's say 60. It could also be a smart pointer to this, but it doesn't really matter. Here it has this thing has a reference count of 1. And adding that into here will lump up its reference count, and it should be decremented when this function exits. I'm not sure. Let me just do this, just in case. But make it return one of those. Sure. Something I have to think more carefully about with these things. I don't think it matters. The reference count and everything is fine because it's a part of the pointer. All the smart pointer interface does is manage that reference counter. Cannot convert to HI function. That's probably true. No, I'm going to fix this up slightly. Maybe this should just take a pointer. Now, if it was just a pointer, I think it would have been fine. Exists but inaccessible. But what if it was just a pointer? Oh, now I got this thing returning smart pointers. No, there shouldn't be any problem with this. This is a function interface, so it should be able to turn that into a HI function, I think. Seems happy. Let's see if there's a memory leak. Okay, so you see it's shifted, its phase shifted. No memory leak, that's good. Now I added something, and that made it go to the, you'll notice, it went to the left. And that makes sense, because at position 0, it's as if we'd already moved to position 60. If this is negative, it'll move in the other direction. Let's make it more obvious. So now, let's see, I could use Gmail text. See, what? Oh, it's gone too far. No, 100. It seems like it went in the same direction. If you offset, it should move. It should go to the left. It should do exactly the same thing that we just saw in this case, and so that means there's a problem, a bug of some sort. Now it's going this way. Yeah, say. If I add 150, let's make it small now. Like am I going more than more than a half wavelength? That could be a problem. If it's 20, that's definitely going to go to, it should shift it to the left, because at position 0, the angle will already be 20, which is what it would be if we were at position 20. So it would appear to have moved to the left. Oh cow. It's completely messed up. Oh, I see. Right. I'm using different units. See how I've got to multiply this whole thing. To get it in the right units. Whoops. In terms of pixels, right? If this is going to be in units of pixels, then I've got to do this multiply by 2 pi and divide by wavelength? Yeah. Well, it's got to be in the same order of magnitude as this guy. Even if that calculation isn't correct. But I'm sure it is. It's going to be all wacky because of these extra factors here. Okay, now it's going backwards 20, see? Now if I set it to minus 20, it will go ahead by 20. Pixels. But you see, now I've got a handy way to insert functions into my graph object and have them drawn. And there's no fiddling around with memory and all that. The pixels are visible. We could do motion later on. I'll leave that for now. What I want to do now is this function interface, I function, with its y of x, is one way of looking at a function. But another way of looking at a function, compose to myself, is this. So what we have here is, I don't know what to call it, but Cartesian form or something. A function is a specific type of thing. Like I said, no loops and whatnot. So that's the Cartesian form. Now, there's another form of a function called a parametric form. And it's not really called a function. A function can be written in parametric form, but you can also write other types of things that aren't functions in parametric form. So let's just call it a curve. Okay, that is a continuous line in moving, or not moving, but a curvy line in space is as follows. What's the standard way they write that? What you have is a parameter. Suppose we have a parameter, single parameter called t, and for each value of t, there is a corresponding point in the Cartesian plane. So what we have, I spelled that wrong, capital I. T math, it's an arrow. P, I want P to look like a vector. I want it bold. Try that. No arrow, no nothing. Well, I mean, it might be smart. Bar? No, that's good. It looks almost right. Usually it's a bar with a little arrow, and I'm sure I can make one. So for every value of t, we get a point in space. And only one, usually. It could be more, one or more. No. Every value of t corresponds to one and only one p. However, the converse is not true. So it so happens that typically for every t, there is only one p, one point in space, but the converse is not true. That means there may be two values of t that give you the same point, right? But 2 points will correspond to 2 different t's. Now it turns out every function can be written in parametric form. Everything like this. All functions can be written in particular if we let t dx, that is, our parameter is going to be the x part of this equation, and we have t maps to the point t f of t so that's a oops, not f of f. That's a parametric form. For every value t, there's a point in the plane, a unique point, given by this formula. Okay, but in general, you could have any. This is one type of parametric form for a curve, but in general, t maps to, let's say, f of t, two functions like that. Okay, and so now that's a generalized parametric form of a graph. And for instance, as an example, if we let f equal cos and g equals sine, then we have t maps to cos of t right? And that gives you a circle, not a wave, but an actual circle. As t increases, the point moves around the circle. So that's not a function, but in parametric form, it's a type of function, right? Where the range is a one-dimensional space, t, and the domain is a two-dimensional space, right? And so we can think of that as a function that maps from one type of space to another type of space, and it is a function, and this particular function has derivatives that for every value t. It does repeat itself, so it's multi-valued unless you restrict t to go from 0 to 2 pi, in which case it's a single-valued function that does one circle around the loop. So the next thing I want to do is make a parametric function and add those to our graph and have our graph draw the parametric functions as well. Okay, see you.